So the next speaker is Sandor Lucky. He is currently working as an assistant professor at the Department of Computer Systems at the EADWS Laurent University in Bucharest. I completely screwed this up. I'm very sorry. Maybe you can tell us later how this is pronounced. He also has a PhD from the same university, which he made in 2015, and he is very much working on active and passive measurements, but also programmable data planes, SDNs, and quality of service in general. And we start with his talk on congestion control in independent L4S schedulers.
Hello, my name is Sandor Lucky. I'm going to talk about an L4S AQM proposal which relies on our Core Stateless Resource Sharing framework. There are traditional applications like gaming, voice transmission, SSH that require low latency for good user experiences. However, these applications generate low throughput traffic that do not build up queues along the forwarding path. In this case, strict priority scheduling seems a feasible solution for ensuring low delay for these selected applications. However, with the technological evolution, applications requiring high throughput and low latency at the same time have emerged. Just think of HD 4K video conferencing, augmented reality, virtual reality, remote control of robots, and so on. In these cases, simple priority-based scheduling is not enough. It's not a good solution since it leads to starvation of normal traffic. So how to ensure low latency and high throughput at the same time? So this is a complex problem and it is affected by both endpoints and the network. The endpoints, we can use different congestion controls. In the network, there are buffers of various sizes and AQMs. Most applications use TCP. Loss-based classic congestion control needs large buffers to have full link utilization. Actually, these loss-based approaches fill the intermediate buffers by design, and thus they result in large queuing delays. Of course, AQMs can reduce the queuing delay significantly, but still, for full utilization, we cannot go below a limit. On the other hand, scalable congestion control enables much finer rate control. It can not only react to the fact of congestion, but its reaction is proportional to the congestion level. DC-TCP and TCP-Prag are two well-known examples for scalable congestion control, but the recent BBR version 2 also implements a DC-TCP-like scalable mechanism. In general, they can reduce the queuing latency significantly, but in turn require ECN support and are too aggressive for the coexistence with classic congestion controls. To solve these incompatibility issues between classic and scalable sources, L4S Internet Service has recently been proposed. It promises ultra-low latency, low loss, and scalable throughput for L4S traffic. L4S flows apply scalable congestion control. Its design goals include isolation of L4S and classic traffic, and it also aims at providing window fairness between L4S and classic flows, enabling their coexistence in the same system. A current state-of-the-art L4S AQM is dual pi-square. We will use this method as a reference AQM in the evaluation section. The main reason behind the incompatibility of L4S and classic traffic is that they require different congestion signal intensities. Dual pi-square solves this problem by applying different signal intensities, ECM marking or drop probabilities for L4S and classic traffic. In a nutshell, dual pi-square maintains two queues, one for L4S and another one for classic packets. L4S queue is controlled by a native AQM, a DC-TCP-like step or red AQM, and marks the packets with ECN congestion experienced. For classic queue, pi-square is a AQM is applied, dropping or ECM marking packets with a calculated probability. However, the two AQMs cannot work independently. The output of classic AQM is also used for determining a coupled marking probability. It is also considered during the ECM marking of L4S packets. As a result, this coupling mechanism leads to higher signal probability for L4S and lower for classic packets. Dual pi-square works very well if you consider a single classic and a single scalable congestion control behavior. It ensures different signal intensities for the two classes but cannot differentiate between the flows inside the same congestion control family. In the recent years, several congestion control proposals have emerged, both scalable and classic ones, and for example, BBR version 2 can also work in both classic and scalable modes. RTT unfairness is well known, but there are further problems. For example, the aggressiveness of congestion controls from the same family could also be different and may raise incompatibility issues. Most AQMs also have an assumption on the congestion control behavior. And what if it is not accurate? Let's see an example for the incompatibility of two scalable congestion controls, DCT-CP and BBR version 2. The left figure illustrates the case when a step AQM is applied, which is similar to the native L4S AQM of dual pi-square. Without going into details, we can clearly see that with step AQM, DCT-CP flows get much higher share than BBR ones. The right figure shows when our in-network resource sharing method is used, we can see reasonable fairness. The key problem is that DCT, CP, and BBR version 2 require different signal intensities. However, step AQM applies the same ECM marking probability for the two flows, and it leads to unfairness. On the other hand, our early Core Stateless AQM proposal can provide different signal probabilities for DCT, CP, and BBR flows. It doesn't require flow identification and flow clues, but this early version of our AQM cannot satisfy the requirements of L4S and classic traffic at the same time. It also requires additional packet marking before the bottleneck. The L4S AQM we propose is based on our Core Stateless Resource Sharing Framework called Per Packet Value, PPV. In the per packet value concept, the resource sharing policies are implemented by a packet marking mechanism that assigns a packet value, actually a simple number, to each packet. The packet value is not a traffic class but an incentive expressing the importance of the given packet in the traffic mix. Packet marking can be done for the different traffic aggregates independently and thus can be implemented in a distributed way. For different traffic classes, we can use different methods to calculate the values of individual packets. The routers in the network then aim at maximizing the total value delivered without having any information on the traffic aggregates and the policies to be applied. They solely use the packet value carried by the packet in the decision on which packet to drop or ECM mark or which packet to forward. Accordingly, in case of congestion, packets with the smallest packet values are dropped or marked with ECM congestion experienced. In the per packet value framework, if we have a flow and we apply policy A, this policy determines the packet value distribution of packets belonging to the flow. The role of packet marking is essential. In the following example, we assume two constant bitrate flows called flow number 1 and flow number 2. The marking is based on a function that we call throughput value function. In this example, the two flows represent two separate traffic aggregates having independent packet markers. The throughput value functions used for packet value calculation are the same. It means that in case of congestion, we expect fair resource share between the two flows. In this example, we only distinguish 10 different packet value levels from 1 to 10 as seen in the figure. For each throughput value, the associated packet value is seen on axis epsilon. The throughput value function defines the expected contribution of packets with given packet values in the total traffic of the flow. In our example, the sending rate of flow number 1 is 80. And in this case, packet value is 10 between throughput 0 and 10 on the throughput value function, which means that if we filter out packets with packet value 10, their throughput share in the total traffic of flow number 1 should exactly be 10 megabit per sec. Similarly, the contribution of packets with value at least 9 is 20 megabit per sec, with at least 8 is 30, with at least 7 is 40 megabit per sec, and so on. The sending rate of flow number 2 is 50 megabit per sec and the bottleneck is 60. Since the same throughput value function is used and the sending rates are high, we expect fair share of the bottleneck capacity. Dropping packets with the minimum packet value leads to an observable packet value threshold below which all packets are dropped. And in this case, this threshold value is 8. And it results in 30 megabit per sec allowed traffic or allowed throughput for both flows. This animation illustrates how bottleneck works in the previous example. Our L4S AQM proposal called Virtual Dual Queue Core Stateless AQM can be deployed in a per packet value domain where the packets are marked with packet values in advance. Similarly to Dual Pi2, it also maintains two queues. L4S traffic is directed into queue 0, while Classic into queue 1. Our AQM method also maintains two virtual queues for two reasons. First, virtual queues can be used for reducing queuing latency in the physical buffers. And second, they can keep histories of packet values used for calculating stable congestion threshold values. Each L4S packet updates both virtual queues with its size and the packet value. If packet size fits into both virtual queues, the packet is anchored into the L4S physical queue. Classic packets only updates virtual queue VQ1, and the packet is stored in the physical Q1. We extend the original virtual queue concept since a virtual queue not only counts the packet sizes, but maintains a histogram of observed values. Similarly to traditional virtual queue concept, VQ0 and VQ1 in our system have a maximum size and a serving rate that is less than the outgoing capacity. Packets are served from the two physical queues with a simple strict priority scheduler, L4S first and then the classic. You can recognize that virtual queue 0 represents the value distribution in the L4S traffic, while virtual queue 1 stores the coupled distribution of both L4S and classic packets. From these distributions and the predefined serving rates and delay targets of the virtual queues, two congestion threshold values can be calculated. CTV0 is applied for the L4S traffic only, while CTV1 for both traffic families. They are simple filters. For L4S packet, if its packet value is above both thresholds, the packet is forwarded. Otherwise, we mark the packet with ACN congestion experienced. For a classic packet, we only check CTV1. In practice, congestion threshold values can be translated into congestion signal intensities. This coupling mechanism is similar to Dual Pi2, and it ensures fairness between L4S and classic flows. Our evaluation testbed consists of three machines connected in a chain topology, a traffic generator, a receiver, and a bottleneck in the middle. We implemented both Dual Pi2 and our Core Stateless AQM in DPDK. NetM tool was used to emulate RTT. We also modified the bottleneck rate between 1 gigabit per sec to 10 gigs. And we use different congestion controls in the generated traffic, and the tool we used is iPerf2. In the first scenario, we compared the performance of the two AQMs under changing traffic intensities using DCT-CPS L4S and QBKS classic congestion control. In case of our AQM, all flows use the same throughput value function, meaning equal desired resource sharing. The experiment consists of 9 phases, varying the number of L4S and classic flows. Each phase lasts 20 seconds, and the number of L4S and classic flows can be seen on the top of the figures. We can clearly see that both AQMs provide good flow fairness even among different traffic classes if the number of flows is large. Our method uses virtual queues that results in slightly lower utilization than Dual Pi2. It's about 98%. Okay, in the first phase, a single DCTC flow is not able to fully utilize the bottleneck link. With our AQM 0.8 gigabit per sec flow throughput can be achieved, but dual pi square results in even worse utilization of approximately 30%. This phenomenon doesn't appear with a single classic flow in the last phase. With one L4S and one classic flows, both methods show significant unfairness. Dual pi square gives larger share to classic traffic. In contrast, our AQM favors DCTCP. We believe that this is mainly due to the difference in strict priority and time-shifted FIFO scheduling of the two approaches. The 19th percentile and the average queuing delays are similar for both methods. Dual pi square results in slightly smaller delays for L4S, but our approach also provides average delays in sub-millisecond order. Except some temporal peaks, significant maximum delay can only be observed if the number of flows is limited. As the more flows arrive in the system, the maximum delay also goes below 1-2 milliseconds with our approach. We also repeated the previous scenario by replacing DCTCP with BBR version 2. We can clearly see that dual pi square cannot control BBR traffic well, leading to increased queuing delays and significant unfairness between L4S and classic traffic. In general, if the number of BBR flows is large, classic traffic experiences a very low throughput share. BBR applies a complex model-based congestion control. We assume that the observed chaotic behavior is caused by that the BBR's model is not prepared for this complex network behavior. With our core stateless AQM, almost perfect fairness can be seen in most phases. The largest deviance is shown for the single L4S and single classic case. The advantage of our method is clearly visible in this scenario since it can automatically learn the congestion signal probabilities of various flows from the observed packet value distributions. Our approach also provides smaller delays for both L4S and classic traffic. Since the propagation RTT on the internet is heterogeneous, we consider a scenario where flows with different RTTs, 5 and 40 milliseconds, coexist in both classes. The experiment consists of 7 phases where the number of flows for each traffic class RTT pairs are shown on the top of the figure. Our AQM provides better but not perfect fairness, while dual pi square cannot handle the heterogeneity and RTTs well. With our method, L4S traffic with 5 millisecond RTT occupies more bandwidth than their fair share, which is more visible when flow starts leaving the system. It seems that DCTCP flows with small RTT can adapt to the new conditions much faster, occupying the freed resources. We also repeated the experiment with BBR's L4S congestion control. With dual pi square, the unfairness between L4S and classic classes is more significant than with DCTCP. BBR traffic almost fully suppresses cubic flows. On the other hand, our Core Stateless AQM provides similarly good performances with DCTCP. The BBR flows occupy faster the feed resources than classic ones, but also allow cubic flows to increase their rate. In the next scenario, there are 4 different congestion controls in the same system. DCTCP and BBR used as L4S and cubic and BBR as classic congestion controls. Similarly to previous experience, we vary the number of flows in the traffic mix as shown in the top of the figures. For our AQM, fairness is reasonable during the whole measurement. In the marked areas, the number of flows is the same. However, the classic BBR flows cannot restore the throughput when load decreases in the last phase. We assume that the BBR's model stuck in a wrong state and cannot adapt to the changed network conditions. For dual pi square, the experience fairness is much worse since L4S BBR flows take the most throughput. It's 10 times more than the fair share in some cases. The behavior of classic BBR flows is again very interesting. At the start, they take a high share, while in the end, they have the lowest share. It is especially interesting to compare the first and the last intervals when the traffic mix is the same, but the resource share is significantly different. We think that BBR's model-based congestion control cannot tolerate the highly changing conditions of this scenario. Congestion control evolution is ongoing. In this wide environment, compatibility of congestion controls even within the same family cannot be expected. We need an AQM that provides different congestion signal intensities for different congestion controls. We have demonstrated that our proposal provides different signal probabilities for different congestion controls by design without the need of flow identification and per flow queues. On the other hand, it requires packet value marking, and thus its deployment can only be feasible in closed networking domains at the moment. The proposed algorithm is lightweight, and we are working on its implementation in P4. Finally, all the measurement results, including the scenarios at 10 gigs, are available in our website. Thank you for your attention.
Okay, thank you very much. It turns out I just broke my video, so you have me without the video. But at least we have Sander here on video and Roland, so you can see them. So very first question from my side, how do you pronounce your university?
It's Eötvös Loránd University. Eötvös Loránd was a physicist.
Okay, that sounds much easier when you say it.
Yeah, I'm from Budapest, not from Bucharest.
I see. Okay, then we would have time for some questions. Maybe I can go with the first question first. So as mentioned on the very last slide, you're working on an implementation. So can you say something about implementation complexity, maybe also compared to the dual pi algorithm?
I think the complexity is very similar to dual pi square. So basically our CTV-based method. So we have this through packet value filters. I mean, at that point, I mean, implementing this is very, very simple because you have the packet carries the packet value, and you only have to check if it is bigger or greater than the actual value. And you can update these filters periodically, similarly to dual pi square, where you update the drop probability periodically. Here you do the same with the threshold values.
Okay, so it's mainly the math that's different, and probably the virtual queue handling is also a little bit different, right?
Yeah.
Okay, then we go to Greg, who's in the queue again.
Okay, thank you. Very interesting work. A couple of comments. One, as noted on your last slide, congestion control evolution is ongoing. BBRB2 is a moving target. Also, DC-TCP in L4S has migrated to TCP prog. Be nice to see evolution of your work tracking those congestion controls as they evolve, maybe rerunning with the current version of prog, that sort of thing. Second comment is be interesting to see a comparison of your algorithm to an FQ implementation that supports L4S ECN signaling as well. That would be really interesting to see, both on the performance side and the complexity side. That's it.
Yeah, actually, what was in our mind? So first of all, our approach has the benefit that we don't need per flow queues. And for example, if you want to implement it in a high-speed router like a barefoot Tofino or something like that, you cannot work with lots of individual queues. So you have very limited capabilities. And in this way, you cannot do per flow queuing. And in our approach, I mean, at the moment we are working on a P4 implementation, so I can say that this algorithm with some simplification can be implemented in P4 and can run on real physical hardware. However, it's of course in the software implementation part, or if we have a software target, it would be also good to compare the results with a per flow or a flow queuing AQM like FQ-Codel or something like that.
Okay. Do we have more questions? Okay, then also thank you for your talk.
Okay, thank you.
And